Good morning. My name is Chris Sidroff. I'm with Applied CCM, and I'm going to be giving a training session on using Pointwise with OpenFOAM. Really talking about best practices for meshing with OpenFOAM. So this is going to be an interactive session for the most part. I have a few slides that just kind of for few key talking points, talk a little bit about Pointwise, kind of what we're going to go through today. Most of it is going to be spent within Pointwise application. We're going to actually run through meshing an application. And just, I hope this is, for whoever's attending, I hope this is a bit of a back and forth. So I'll there'll definitely be a few points where we can stop and answer questions and things like that. If there's any questions to be answered. So go ahead and, ask your questions whenever you feel like you have one, and I'll do my best to answer at that time. So let me just put my slides up here. Okay, meshing best practices for OpenFOAM and Pointwise. Okay. So again, mentioned we're going to be using Pointwise. It's a meshing application that I happen to represent here in Canada. So just what is Pointwise really briefly? So Pointwise is a pre-processing / meshing tool predominantly used for the CFD world. And the one thing I really like about it, it really kind of adheres to the Unix philosophy where we do one thing and we do it really well. It's really all their focus has been, they don't have a solver, they don't have any post-processing capability. It's really about meshing for mostly for safety analysis. It can be used for other applications as well. So I just got some nice images of meshes I've made over the last few years. I should also mention that Pointwise was previously a small independent company based out of Texas, US. It was earlier this year was purchased by a company called Cadence. So Cadence is now owned by Pointwise. And I'll just leave this slide up here for a few seconds to kind of just a brief kind of feature list of its capabilities, importing wide range of CAD formats, the open format IGES and STEP, as well as half a dozen or more proprietary formats. So the ones you find are the most popular CAD softwares. It also imports discrete formats such as STL, OBJ, PLY. It has structured meshing capabilities, so very traditional structured meshing, so like all hexahedral, multi-block. Obviously a little more popular these days is the unstructured meshing, and it can actually combine the two together in one mesh. And I'm actually going to cover that a bit today. We're going to do most of the meshing is going to be unstructured, and then we're going to do some other regions where we're going to take advantage of structured meshing just for cell count, cell quality. If you're also into overset meshing, it has that capabilities and interfaces with a couple of popular overset grid assembly softwares. And it also has the ability to kind of read in overset information so you can visualize on top of the mesh. And like I mentioned, it can do hybrid where you can combine any of the above mesh types simultaneously together. The other thing that makes it, I would say, very flexible is that you can save your mesh in a huge range of CFD and FAA formats. I think there's like over 60 at this point. But as you can imagine, the most common ones: OpenFOAM, Fluent, CFX, Star CCM, CFD++, Cobalt, ANSYS, et cetera, et cetera. There's a huge range of them. And even for the ones that aren't there, there's an API that allows you to, write your own grid your mesh exporter. And then really popular is the scripting interface where you can automate. You can do all sorts of things. You can do utility stuff, but you can do fully automated meshing through its Glyph scripting language, which is originally traditionally more uses TCL or TICO, but there's also now a Python interface as well because of the popularity of Python in this case. So what I'm going to talk about today is actually I'm going to go over meshing the FDA blood pump model. But I've actually given a few talks at at some past workshops. So way back in 2011 at Penn State, I gave a similar talk when I actually formerly worked at Pointwise, and I was talking about structured meshing for trading machinery type applications. Talked a little bit about mesh quality metrics. I'm going to kind of cover that again today. I also, in 2015, when I started my company, Applied CCM, I was did a talk at the University of Michigan, and this is a little bit about how do I say it? I was talking about interpolation and non-unplugging reflection schemes. The word I was looking for is discretization schemes, and this is in our group with OpenFOAM called Kayla. So I was kind of talking about meshing related stuff, but more from the library side and less so from the meshing side. And then last year we presented our work that I was doing jointly with Pointwise on the actual simulations of the flow in the FDA benchmark blood pump model. And we were talking about different meshing strategies and the results of that, and some of the software that we developed through the Plexus here. So what I'm going to talk about today, or go over today, is we're going to go over those mesh quality metrics, kind of from a practical standpoint. There's obviously a huge range of mesh quality metrics that you can use to evaluate your meshing on foam. I'm going to cover the three most common ones, and typically what you look for when you're checking the mesh. Most of the time, I'm going to be spending building a hybrid mesh of the blood pump using Pointwise, and then some of the pre-processing steps before actually running your simulation with OpenFOAM, and some of the important things, because it's in reality we have to deal with creating meshes with unstructured meshes, whether it's Pointwise or some other commercial mesh or open source mesh like Snappy Hex Mesh or Swift Mesh, and we all know they're not perfect. They don't always generate these perfect meshes, and so we have to come up with strategies to mitigate both, making the meshes as good as possible, and also just dealing with, the non-perfect nature of the meshes, and what can we do from a solver and visualization point of view. So mesh quality. So how do we determine what a good mesh is? So this is a quote that I actually pull out of my talk from the Penn State slides, and it's from quite a while ago, but I still think it's pretty interesting these days. Is the standard rule of thumb is that the element shape should be pleasing to the eye, and it almost seems like that. It's really hard to kind of precisely define what a good mesh means, because it can vary from mesher to mesher, or from solver to solver, or even application to application. And like I mentioned, so there's no single standard benchmark or metric that succinctly assesses the quality of the mesh groups. And as we've all know, grid dependency studies are good, but they're not trivial. They're really hard to do, because the enormous amount of computational resource they can require, or even just doing something as simple as by doing the grid dependency study, where we have kind of a hierarchy and family of meshes. Those meshes themselves may bridge different models, so we can't even compare apples to apples, because, for example, the mesh resolution in the coarse mesh requires a wall function for the turbulence model, but the fine mesh is such that the wall function is no longer needed, so it can be hard to do that kind of stuff. So helpful and good, and we should strive to do them, but they're not trivial to do, that's for sure. So we just rely on suggested best practices. I hope I can give some today, and some of our own experiences. So we're just going to go over, I'm going to talk about three of the common mesh quality metrics that I typically use for my day-to-day work. So the first one is aspect ratio. When I say the three most common that I would look at with OpenFOAM. So we're going to look at aspect ratio. So this one, we obviously commonly have high aspect ratio meshes, because we try to pack the mesh in the direction normal to the wall to help us resolve the boundary layer without unnecessarily increasing the cell count. Not necessarily, but again, dramatically increasing the cell count. And in general, like high aspect ratio meshes are okay with OpenFOAM, you know, especially if the gradients in the long direction are small. So in this case, the direction, the horizontal direction was small relative to the vertical direction. I mean, I forget what check mesh will warn you about in terms of aspect ratio. I think it might be around 1,000. I think it's 1,000. And you know, and that's okay. You can have an high aspect ratio mesh, and I've even ran meshes with aspect ratios well over 1,000, and gotten perfectly good solutions and found good convergence. Now there are some situations where the aspect ratio may come into causing some solution difficulties in terms of convergence. I would say it's probably more common for, or at least where I see it, to be in the marine world where we want to run not model scale but full scale simulations where a ship or a submarine, which is has a very high Reynolds number, but yet we're trying to resolve the mesh into the wall, and we're trying to keep the mesh count down, and it's not uncommon to encounter aspect ratios that are well over 10,000, and those can be challenging. So anyways, so I should also mention here too that the actual definition of OpenFOAM of the aspect ratio is we take the Cartesian component aspect ratio, which is the max Cartesian component over the min Cartesian component. So that's the component aspect ratio. And then we also compute the hydraulic area aspect ratio, and we take the max of those. So that's the actual definition of aspect ratio. Okay. So the two main ones we're going to look at aside from aspect ratio that we're going to probably attempt to fix are orthogonality. So by definition, it's the angular deviation of the cell center vector from the face center vector, and it predominantly affects interpolation of the gradient to the face center, and because it tends to affect gradient reconstruction, it's going to affect the actual dilution terms. And so where this is going to show up for the most of us, I mean, OpenFOAM is used for a huge range of applications in compressible and compressible, but compressor solvers will probably be where you run across it the most. And so it's our friend the pressure equation, which is a pressure Laplacian. And so this is and the pressure Laplacian is very important for flows where it's responsible for both satisfying, correcting the momentum equation, getting the pressure field, conserving continuity, this kind of stuff. So getting a solution of the pressure equation is key. Non-orthogonality can cause problems for that. The second one, it would be the skewness, and the skewness is the deviation of the cell center vector from the face center. So you can see on this diagram here what I'm talking about. So the midpoint rule is second order accurate if interpreted the face values are at the face center. And so this tends to affect face interpolation. So things like convectors are affected by this. So kind of before I get to the demo, I just wanted to make kind of a point, like kind of goes back to what I started with, is that, I talked about, it's really based on experiences to what's a good quality mesh and what we need to get a good solution. And I just kind of put the question on, are aspect ratio skewness on orthogonality sufficient? So you can see here that in both of these meshes, aspect ratio is 1, skewness is 0. In both cases, I mean, if you just do this diagram, right, so that that's the case. However, I'm pretty sure everybody would feel way more comfortable running the mesh on the left with the square cells than you would with the cells in the right, with the triangle cells. It's just kind of like our intuition says that we would get a better solution with the mesh on the left. So, anyways, so I digress. So I mentioned that we're going to go over meshing the blood pump. I wanted to throw up the slide really quick in terms of a mesh summary from this is actually from our work last year, from the workshop presentation last year, where we presented the meshing on the pump using structured approach versus the hybrid approach. And I just really want to highlight the amount of time it takes to make the mesh. The structured mesh took on the order of almost a week. So 40, 45, or maybe even more than like 45 to 50 hours. Whereas the hybrid mesh took 2 to 3 hours. And in fact, since I only have about an hour and a half today, probably at this point, an hour and 15 minutes, we're going to actually do it far less than 2 hours. So there's been improvements in Pointwise in the last couple of years that we're going to get very close to this hybrid mesh I did last year, and we're going to do this in about an hour. Okay, so I'm going to at this point I'm going to fire up Pointwise, and we're going to run through the little demo. Maybe I'll stop at this point and just check to see if there's any questions that anybody wants to answer at this point. No questions yet. Take a bit of a break. I'll start out Pointwise and then we'll go from there. I think the other one I'm going to do here is I'm going to share my entire screen. So apologies if I kind of flip around a little bit, but I have a terminal window open and the Pointwise application open. Okay. Don't see any questions yet. I guess it really has anybody said that's probably controversial or warrants any questions, but I'll move along anyways. So let me just show my entire screen. Okay, so here's the Pointwise application. So the first step, what I'm going to do is I'm going to bring in the geometry. So from the FDA website, you can go and dig this up. This is all openly available information. So I'm going to start right from their the basic geometry. So they provided them, I think, in a handful of formats. I'm going to load in the step file. So I previously loaded this up into Pointwise, so I'm just going to go and pick them from my most recently used list. So there's two parts to it. There's the pump housing. I'm going to stick this in its own layer, just so because we're going to work on a little bit of organization. I want to also point out that Pointwise kind of reported to me in the message window that the model size was adjusted to 10,000. There's something I could be aware of is that the units that they built the geometry in was not even units of millimeters. It was units of like 1e to the -4 units. So like effectively like, 1 decade smaller than millimeters. So we'll just have to be aware of that when we go to run the mesh, and I'm going to cover that a little bit. We have to scale up the mesh by unit of 10,000. And once we're done in Pointwise, I could scale it in Pointwise, but I tend to like to leave the geometry as built, and then we just do the mesh scaling within OpenFOAM. All right, so we have the housing geometry here. Name that layer housing geometry. That's in layer 1. I'm going to load in the rotor geometry. Put it in layer 2. I like to organize a mesh as I go along, just to kind of make things easy. This is just warning, it's just asking me about renaming some piece of geometry. What happens is when Pointwise loads geometry, it like automatically assigns names to them if they're not there. Not super concerned about naming at this point. The other one is change the color of the geometry. I'm going to show the problem. So a couple of things I'm going to do before we kind of get going in terms of meshing is first I'm going to set the CA tag. I mentioned at the start that Pointwise supports all these different flow solver formats. It's not going to have a big impact right now. We're going to do this a little bit later in terms of like setting up the boundary condition stuff, but I think it's just a practice I like to do. So anyways, here's the list. all the solvers, of course, I'm going to pick OpenFOAM. And one more thing I'm going to do before I get going is I'm going to set some default orientations, because I'm going to kind of, as I work on my mesh, I may want to look up on the top of it, I may want to look down on it, up on the side, or I may want to look at some sort of nice kind of perspective. So I can use the little orientation keyboard to kind of do this stuff, but those aren't too bad. But I find that I think it's the X one that kind of puts up the side, and I also want to kind of go back to a nice perspective view. So what I'm going to do is I'm going to set my rotation point, and just set one from the side. So I'm going to assign this. I'm going to assign this to a custom view. So you can't see me doing this, but I'm using my keyboard shortcut. It's just Alt-1. You can see I start using V1. So now if I rotate around to some arbitrary location, I can just do Control-1 and it takes me back. I'm going to do the same thing from the top. So user V2, so rotate around. And then the last one I'm going to do is I'm going to set myself up on this perspective view here. So it just kind of puts me back to this, and I'll save that as. So if I go back, I can get really quickly back. Okay, so a couple more things we're going to do. So in this case, I worked this geometry previously. I know it's a pretty clean geometry, but we can check that. We can look at the actual the model in Pointwise. So the word for that in model in Pointwise is kind of analogous to like solid. So if you're looking at CAD software, you would probably use the word solid or something like that. Pointwise calls it a model. And we have a single model. We can just kind of check it really quick just to make sure it's assembled. If there was actually holes or some edge on it that was not assembled, we would see some lamina here is just a mathematical thing for like an edge that's only used by one surface. So we have a nice watertight model here. I can do the same thing with the. I can do the same thing with the housing. Okay, everything's good. I don't see any lamina boundaries, so we have some nice watertight models. The one thing that I'm gonna fix here a little bit though is so how Pointwise works is it's a top-down, a bottom-down measure. So it works by we start by creating grid pairs, which it calls connectors, then we make surface meshes, which it calls domains, and then we finally assemble the volume mesh, where we use blocks. We assemble the blocks in those domains. Now there are some ways to shortcut that. We're gonna have Pointwise kind of automatically make us domains and connectors on our geometry. But what it does is that on the edges of the actual surfaces, the geometric surfaces, it's going to create connectors. So this is one of the nice things about Pointwise being the top, bottom measure is that getting your grid points on the features in geometry is kind of automatically part of the process. We don't have this kind of snapping process or a geometry conforming process that the top-down measures do. But one thing that can happen is that we often find that there's just kind of, it's a byproduct of how the CAD software decides to make the geometry, which isn't really like help us from a solution or meshing standpoint, is that it creates kind of unnecessary number of surfaces. So for example, on the rotor here, we can see that like on the fillets and on the rounds, we have like, there's two surfaces. It was just split for some reason. And you don't really need a grid pair. You don't need points there automatically. We can easily kind of constrain the mesh to follow the curvature anyway. So it's just going to go in the way of. So what I'm going to do is we're actually going to join up these surfaces into single surfaces. And so it'll take a few minutes just to go through it. And it's mostly these fillets and rounds on the rotor blades that where this is happening. So again, just for the sake of time, I'm not going to kind of go through and detail describe everything I'm doing. I'm selecting the list of my process, but I'm just trying to give you kind what the kind of the process would be for. So again, I'm just gonna select these pairs of surfaces. What you're going to do here is that I'm going to join these together into a single surface, so that when it will be a little more obvious when we go to put it in the geometry. So, I really just want to, first step, I really just want to clean up these rounds. Fillets. And I'm going to click this button, which just called assemble quilts. So what we'll go ahead, so I did that really quick. So it's funny. So I assembled the quilts and it said assembled 64 quilts into 32 quilts. Now it's funny that I can still see the edges. So the edges of the actual geometry doesn't go away, but Pointwise sees that as a single quilt. So quilt in Pointwise terminology is just it's a region where it's expecting to create a surface mesh. So again, it's not super obvious right now, but if I were to go ahead and mesh this previous to that, it would have created a single surface mesh on each one of those long, narrow regions. But now that I've joined it up, I'm going to get kind of the. I'm going to do it in a couple of locations here too. We'll do it on the rotor head. So just okay, so I think I pretty much got it. So I think I've kind of tidied up my geometry a little bit in terms of creating the mesh on there. So maybe let's do that right now. There's some other geometry steps that I need to do, but I'll do them after I mesh this. After we do the mesh on. Okay, so I'm going to pick the model. That's the model, is the watertight representation of all the surfaces. And we'll go ahead and create a mesh on that. So I'm going to use the automatic surface mesh capability in Pointwise. So this is what's changed since we originally did this web pump model. This is probably why I can do this mesh now in less than an hour, whereas when we originally did it probably took us a couple hours. So what this does is the automatic surface mesh capability. It does some sort of it does a bunch of geometry interrogation to help determine the scale of the mesh based on the size of the geometry and how we want to resolve it, all that kind of stuff. So we can do that in two ways. We can do it by subdivision, or we can do it by edge length. I like to do it by edge length because it kind of makes the fence. So it's and again, these numbers are it's automatically getting from geometry set. So it's got some sort of minimum boundary length in this geometry is 0.757, and so it's determined based on the number of subdivisions, determining what the edge length should be. 2, so the edge length is going to be half of this number. So that's what this comes from. The max edge length, its default is 150 subdivisions, and that results in a max edge length of about 4. And it turns out that 4 is a pretty good number. The one that I'm going to change is the fillet resolution. One is going to mesh the fillets and rounds. I like to have a little bit better. I'm going to go 10 degrees. And I'm going to go to mesh that. And then, yeah, that's pretty much it. So the next step is now I'm going to leave the aspect ratio and the boundary. And these have to do with the surface meshing. One of the surface meshing algorithms, excuse me, is that where it needs to, it can go kind of layers of cells to help resolve the geometry. And I'm going to leave the aspect ratio of 10 and one other thing we'll go through really quick is things of the geometry derivation is under the analysis that it's trying to kind of find regions of curvature or regions of a convex and concave, and it's going to try to apply some sort of in this case here, I don't really want to use it because I kind of want my mesh to be somewhat, uniform. I don't really. Whereas maybe if you're doing something like, aircrafting or something like that, but it has some really long single services, and you want to really kind of optimize the point placement. So I'm gonna turn that off at least on this contact edge, which is the bottom of the rotor shaft. But I'm going to leave it on for the curvature reasons. So I'm going to go ahead and I'm going to help to generate the surface mesh. We're just going to go right to this. Is going to probably take about a second. My laptop's pretty old now. It's quite old. So I assume something really happens next time. And I would say your mileage is going to vary as to how much it's going to take, depending on the complexity of the geometry. Or something way more complex than this is obviously going to take a while. And you just have to get out of the copy or in this case we can do something like oh, we can bear that. Apologies. Just let me know if you can. If there was a question, if somebody could bear it for me, I just see if I could turn on the mic a little bit. There was a question about can you come on in different ways of computing skewness, informers, and in check mesh. And besides, what max value of skewness would you advise? So in Pointwise, the skewness measure, that's actually a very good question about skewness, because it's a very generically used term in the meshing world. If you go from mesher to solver to developer, everybody kind of has their own kind of definition of skewness. So I defined what it was, at least in OpenFOAM, and it has to do with the deviation of the vector connecting adjacent cell centers with the face center. And again, that really has to do with our approximation of the midpoint rule. In the midpoint rule, it's like our surface integration, where we're assuming when we're integrating on the surfaces of the cell, we assume it's at the center of the face. Yeah, but in Pointwise, there's a wide range of different skewness measures. And maybe when I go back here, I'll finish answering that question in a second. Let me just share my screen again. Okay, so I finished the mesh here on the rotor. Excuse me. I'm going to click OK. I'm going to finish before I finish answering this question about skewness. I'm going to take all the mesh. I'm going to put it on the foam layer. Stick it in layer 102, so basically like 100 layers above the original one. So I'll just roll the mesh. Turn off the geometry. Change the shade of the mesh. You can look at this. So yeah, so the question about skewness, so I go to the examine menu, and Pointwise has a huge number of examine metrics. There's a whole bunch of here that have to do with skewness. Echo angle, echo area, echo volume, centroid, anyways. So again, because skewness is such a kind of generically used term in the CFD world, you really have to kind of go to the documentation for whatever application you're talking about to find out what that means. But when I say skewness today, I'm talking about the OpenFOAM skewness that yeah, I'm talking about the OpenFOAM skewness, which again has to do with the deviation of the cell center vector from the center of the face. I'm not going to be using any of the skewness metrics in Pointwise. And there is no kind of corresponding skewness, equivalent skewness metric in Pointwise that we can use. So we're going to have to depend on check mesh to look for skewness within Pointwise. However, non-orthogonality, there is an equivalent non-orthogonality. So down here, we're going to use the non-orthogonality, cell non-orthogonality. We're going to use that later on when we get to our volume mesh. We're going to use that later on when we get to our volume mesh. Okay. So we finished our rotor mesh. Now, let me turn the housing geometry back on. So we have our rotor mesh done. We're getting close. Now, something we haven't talked about at all is our, how do we manage, how do we want to set up our simulation? So we wanted to set up a simulation to do, well, we can do this one of two ways, because we have, we want to model the rotor rotating. We can do that in two ways. We can either do it with a moving reference frame model where we just apply the source term into the steady state system of equations, or we can actually dynamically rotate the model. So either of those approaches, we're going to need to create another region for the rotor where it moves. So what I'm going to do is we're going to chop up, not really chop up, that's a bad word. I'm going to split up the rotor geometry, and not the rotor geometry, excuse me, the housing geometry to kind of accommodate that. So what I'm going to do is, if I just look on the side, is that, so I'm going to kind of create a region just above the top of the rotor. I'm going to kind of split the geometries above it, and I'm also going to create a cylindrical region between the outer boundary of the rotor and the housing itself, because I want to create that interface that we're going to create. We're going to need to create an AMI boundary between the rotating region and the non-rotating region, and also here at the inlet as well. So I'm going to accommodate at that Pointwise by splitting the rotor geometry, the housing geometry. Excuse me, I keep saying that. My bad. So the first step is I'm going to create a plane. So we're going to create a plane. We're going to use the plane to split the geometry. I'm going to create a plane in the Z direction. And I can't remember what the number is. Let's see here. I'm just going to enter an arbitrary value. Just turn the rotor back on so we see where the heck is. It's probably a little bit too close. You can see the yellow is where the potential plane location is going to be. So 250. That should be enough room to allow the mesh to kind of, because what's going to happen is I'm going to split the geometry here, which is good. Split the geometry. So that kind of create that split over there for a second. Anyway, so what I'm going to do is I'm going to create a mesh above and below this. That's going to be kind of the static mesh. Excuse me. Because we're going to want to create we're going to need to create a cell zone or a separate region that we can apply the MRF term, or we can dynamically rotate the mesh. And then based on that, we can set the appropriate bounding conditions on the wall of the point itself. Okay. Next step now is we need to create, so we look straight down, and I need to create a cylindrical region that's kind of halfway between the outer boundary of the rotor and the housing itself, because we need for this kind of to be able to create this interface region. We're going to create an EMI there. We put the mesh there. So what I'm going to do is I'm going to create a cylindrical piece, a cylindrical object. I'm going to make sure it's a database. I'm sure you can't speak this geometry. I happen to know that the axis of the rotor is long. X, Y at 0. I'm going to place it slightly below the bottom. This is the part we're going to change the radius. So 300 looks to be about, that's about the radius of the housing, so which is similar to the 50. 75. Okay, so you can see that it's getting pretty close. I think 280 is about half of the thing. So if I'd have had the actual order down and everything like that, I don't know exactly what the point is. So we can just, and then what I'm going to do here is I'm going to change the unpredictability. So I'm going to, that's why I created the point of it a little bit below the geometry. I'm going to create it a little bit above. And it's not obvious that the reason why I'm doing that is I kind of need this new surface, this cylindrical surface. I need it to pierce the bottom and the top of the housing, because when I do the cutting, I want it to, you know, for the trimming to work. I'm just over exaggerating it for the purposes of the trimming operation. So what I'm going to do is I'll trim that. So you can see, I see the purpose of over exaggerating. Trimmed it above or below. Split it. You can see different colors here on the rows. Now, what we'll do is there's going to be some unnecessary pieces above and below that. So, not very clear, but there is actually a surface around it. Pause the showing for a second. I'm just going to go back to the questions. No questions. Lionel, let me know if just send me a comment or a question just to let me know if the line is better enough. You know, I'll just check the answer. Let me know if you've got any more questions about schemas. Again, I'm going to talk about this a little bit more. Okay, so we've done some modifications on housing to kind of facilitate the analysis we want to do. We need to create this region where the rotor is either going to move through a model approximation or actually physically move. So we want to create two separate mesh arrangements, and we can accommodate that in Pointwise. So we need some quick modifications to the geometry, and the next step now will just be to go ahead with the actual mesh. So let's turn off the rotor mesh. So better housing geometry. So we actually created a little bit of geometry when we initially made the. So I'm going to actually put that in a layer. So because how it works in Pointwise is that the current layer has the little green triangle, that's layer 0. So anything I create is automatically going in there. So it's kind of like the default. You could change that if you wanted to. You could set a different default layer, but the way I like to work is just this little layer, break images in there, and happy with what I have. I just move them into. So we're going to use the same tool that we did before. Surface mesh. Got the same parameters we did before. This time here, I'm going to turn off. I'm going to make sure all the anisotropic 2D layering is turned off. I don't want to use that at this point. I just want everything to anisotropic. That might take a few seconds to do that. So So again, this is the general process for making these meshes. So maybe I should, while this is doing this, just back up. So how it used to work before there was this automatic surface meshing capability where it would do some interrogation of the geometry itself is that you would just, user would just pick a default value for the spacing and it would just apply it. Would just apply it uniformly, and then you have to go out there on your own on kind of on a region by region basis and adjust the resolution based on the size of the geometry or whatever. Um, you know, whereas now this automatic surface meshing capability is kind of does a lot of that analysis work for us. So we kind of get to what we want a lot quicker. So it's kind of like I look at it before it was like all on you. You just made the mesh and then you get this manual work kind of adjust the resolution. Now I'd say it's kind of giving you about 80% of the way there. Sometimes that 80% is good enough, and then other times, like we're going to do today, intervention. So that's what we're going to do today. So that took about 30 seconds to finish. So let me just finish that here. So looks like there's a question. So there, so kind of my voice is still unclear. I really apologize for that. We'll get my computer closer to my mouth. Let me know if it's still unclear. And I'll try to adjust my microphone. So apologies for that. So just I'm going to pause for a second here. Lionel has a question. In Pointwise, it's sometimes difficult to fill in closed volumes dominated by a bunch of domains. Cells have very bad schemas. So you have tips and tricks for this configurations. Generally happens in internal geometries. It becomes difficult if the domains are a mix of structured and unstructured. Great question, and this is exactly what we're going to work on today. So really quickly to answer your questions. So filling in a closed volume. So generally speaking, if your geometry is watertight up front, like it is here today, and you're meshing the models, then making the mesh and the domains and everything to create a watertight representation is kind of falls out of it automatically. If not, I think I can't remember how this goes in this case, but I think I'll show you kind of the manual way to assemble blocks to help you identify regions where there are issues where the mesh is not closed. And the question about bad schemas, in this case, it's going to be, I'm going to be looking at wrong about the number, but anyways, where the mesh is bad, I'm going to go over a situation where that happens, and we're going to do something that it's going to help us kind of mitigate that. So, so maybe wait about, I think it's going to maybe about 20 minutes before I get that point. I know if I haven't answered the question sufficiently. So Ivan's got a question about, do you have any advice on how to combine structured block with high aspect ratio cells with unstructured block? Yes, I do, and I'm going to cover that here as well. So I'm going to go ahead and answer, mark that as answer, Ivan, but if, after I go through that step, if I have to answer the well, I'll have to answer the question. I'll come back to it. Okay, so let's get back to it. So okay, so again, mesh organization. So okay, so I have this mesh on the housing now. What mesh we want. So we have. So at this point, we have a watertight representation of both the housing and the rotor region. Well, almost enough place. So I'll get a second. So what I'm going to do is here. So one thing that's going to be pretty obvious, and I could have done this, went through this entirely unstructured, found out that there's a better way to do this, come back and review this. So just for the sake of time, I'm going to preemptively kind of change this. So this kind of goes a little bit, Ivan and Linus questions about mixing structured and unstructured. So you can see both the outlet duct, the outlet pipe. So from the end of the diffuser all the way to the outlet, it's like this nice straight pipe. and also from the inlet, just above the rotor hub, and really this is going to be a rotating region below this. From the inlet all the way down is like this, basically this very, fairly simple piece of geometry. So we're actually going to, I'm going to go ahead and create a structured mesh in this region to really, I think the big one, I think is just going to be saving on cell count, because I'm going to create these hex cells and it'll be all aligned with the geometry. And then we're going to mate that up with an unstructured mesh. So what I'm going to do is I'm actually going to delete all these structured domains, unstructured domains. I'm going to delete them. I'm going to leave the actual connectors there because I'm going to use these connectors to build the structured mesh. And I'm actually going to toggle the mesh type right now because I'm going to make sure that my structured. So I'm going to do a couple of things here. What I want to do is, so first of all, I'm going to change the number of points on these. I'm going to reduce the number of points because that's one thing nice about structured. It is much easier to kind of create long stretch cells without adversely affecting the cell quality. So I'm going to change the resolution of these. I think they're like 4. Change them to 4 times 16. Make sure I'm going to do that with these as well. 16. So the other important thing to note with structured domains or structured meshes in general is that opposing edges or opposing places have to have the same number of points. So I want to make sure that these two curves have the same number of points. The top one is 96, the bottom one is 84. So I'll just change the number of points to 91 on both. That'll become obvious in a second. We also here is that these semicircular connectors here. I'm going to just make them all a nice round value of change them all to 51. Why do I choose 51? Because it's the number of points. So 51 will give me a nice even number of intervals of 50 because it's the number of points minus 1. So if I choose 51, I get 50 intervals. So change it to 51. So now I'm going to go ahead and I'm going to do this kind of making these structured blocks. I'm going to make this in a 2-step process. I'm just going to do a quick assembly of the domains and then assemble the blocks. The bottom half. You can see that making structure meshes is kind of a bit of a manual process. So there are maybe structure domains on the bottom half, and on the other half. So the sides of the pipe now are structured. The other thing I need to do is I need to cap off. I need to cap off these ends with the structure domain. Actually, I can't do that by way, excuse me. The reason I can't quite do that yet is because to make a structure domain, I need to have 4 edges. And right now at the circular regions, I only have 2 edges, so I need to split these connectors into 2 pieces. Pick each of these semicircular connectors. There is a tool for doing this. Under edit, I can split the connectors into a fixed number of pieces. I already have this paper in the toolbar, so I'm just going to go down and split each of these connectors up into 2 pieces for me automatically. Now I can select these groups of 4 connectors. Select these, and what it's going to do is it's going to create the structure domain. Now you can see right here at this point we have a structured domain, but this is not what we'd like in terms of like. So you can see just the character of the mesh is it's going to be really hard for us to be able to kind of pack the mesh near the walls. Anyways, the short story is that we want to move to, if this is a single block approach, we want to use to a multi-block approach for all. So terminology we use this one in this, we call it butterfly approach or or an OH approach or a 5-block approach, whatever you want. So, and I apologize for the bad mic. I'm not sure why that was the case. I'll just let me. I'm going to control with the conference. Okay, I'll get back to you on the phone. I apologize for that. I'm not sure what's going on. Just have a quick chat with the conference organizer. Anyways, well, he gets back to me. Anyways, it's okay. So I got to convert this. So first of all, so just bear with me. We have this kind of non-optimal structured mesh situation, but I'm gonna convert it. So what I'm gonna do is first I'm gonna assemble these. Some of these blocks, these structured blocks. So what it's done, so this is kind of some funny business here at these other regions. And the reason why Pointwise just kind of messed up the mesh a little bit is because when you make domains or surface meshes in Pointwise, it will automatically try to constrain the interior points of the domain. And because in this situation, the connectors resided on the geometry, but there's actually no geometry kind of in the middle where the circle is. It's gone and projected the points to the boundaries, which is not what we want. So we can just turn off. We can turn off the shape projection, and we can just go back to the left. I'm just going to get it call it uncontrolled. Messed up. You just put up these different versions. As you can see, so the structure is do the structure measures and the process. And we definitely have the benefits, but and in this case, I think it's one that is going to take us maybe about, I'm not sure when it's to go ahead and make this, but it's going to save us. I can't remember the savings account. It's all kind of like, but it was if I did this with an unstructured, these pipes, I think there was about 3 or 4 million cells worth of different data with about 1 million cells in the situation. Uh, any of the delegates out there, like online, just a question: are you listening or watching? What web browser are you using to listen to the talk? The reason I'm asking is I can use Firefox, and I found that audio quality is pretty bad in Firefox, and I switched to Chrome. Audio quality got better. I'm not sure if that's a problem, but okay. So let me get back there. So the tangent. Okay, so let's fill it our 3 blocks. Over the 3 blocks here again, but if we were to just kind of quickly look at the mesh quality, just look at we're going to get pretty high non-orthogonality. Now for a structured mesh, we should really get very high non-orthogonality. It's all because of these. We just use a very basic topology. So we're gonna anyways. My point is that we're gonna So there is no real kind of easy way within Pointwise to kind of convert this from an H to an OH. However, there exists a script. So I mentioned Pointwise scripting language Swift. There is a utility script that you can find on the GitHub repository called Butterfly Maker, which will convert. I'm going to run this Butterfly Maker script, and it will convert all these blocks into an OH topology. Before I do that, I need to change the computational direction of each of these blocks. The reason is because I want to only do the OH topology in a certain direction, so I need an OH. So I'm just going to swap the directions here. And I'm just doing this because I'm just trying to put the I coordinate. This will make sense in a second. I'm just trying to put the I coordinate along the axis of the pipe. So now when I run this butterfly maker script, and I put these blocks, I'm going to just tell it to propagate that butterfly topology in the I direction. So the I computation. So now when I go to this, will take a little while to run. Click OK. So let's get that. Any comments on audio quality? Again, I apologize. I don't know. I'm not sure why I said that. It's when we were preparing for this presentation. I maybe something before. Maybe sped up things for me to go back to my slides. So we talked about there was a question about skewness before, so I'll look this one. So again, so the skewness that we're going to be talking about is the OpenFOAM definition of skewness. And it's this value here, which is like, okay, this is our mesh, here's our cell, the black dots are our cell centers, we have this vector connecting our cell centers. When we do linear interpolation, that's it's the most commonly used interpolation, is that there's this assumption that when we do that interpolation, that it lies at the cell center. Implicitly, if it doesn't, we incur some sort of error. So that's really what skewness is making. If you notice, it kind of happens in these kind of kink regions. So generally speaking, you're not, probably with most unstructured mesh generators, you're not going to get this kind of interior mesh. Where these regions really kind of pop up is on geometry, on the geometry itself. So, and the way we can fix this is that you notice is that it's maybe not obvious here is that this grid point here and this grid point here, if we refine it and move it up closer together, that actually moves the cell centers higher and then moves that block line closer to the base center. So the way to kind of fix skewness is to refine your mesh in those kind of like things. So this, we're assuming this is a piece of geometry. This would be a highly concave, highly convex corner. Is that we can that's how we can fix skewness. All right, so let me go look at this mesh real quick. So now it's kind of clear that we want there. So we have this kind of 5-block topology, OH topology. This is what we want. So what I'm going to do is I'm going to take all this mesh I just generated. I want just the inlet region. Okay, so what we got now is so we have this interface, so we have this structure domain It's going to cap off our unstructured region. Looks like the butterfly is kind of messed up this region. Anyways. Speaker is talking. I'm not sure how long this is. Can somebody just send in a question right now to let me know if you can hear me, everything okay, or if the audio quality is so bad. Yeah, I apologize. Line. I'm not sure why that's the case. Is it just crackly, or is just the volume really low? Just take a quick break here. So the last step will be here when this finishes up is that we're going to mate up the structured mesh and select values. I'm going to have to get from the clicker here. So I'm just the layer. Put this in there, outlet mesh. There we go. There we go. So the last step before we kind of get rid of the structure meshes that we want to, this is coming to go to Ivan's questions before, is that we're going to, I'm gonna pack the mesh near the wall in the structure mesh. So the first step I'm going to do is I'm going to set the wall spacing explicitly. You have to use your structure meshes. Set the wall spacing explicitly, and then I'm setting to the values that we're going to end up mating the unstructured mesh to. So, do this really quickly. What I'm doing here is some things in a second. I'm going to set the spacing values near the wall. This, spacing. Get a value of 0.1. This works for this case. Oh, I forgot to resume my screen. I'm sorry. Okay. It's set the spacing here. Become obviously the new I'm doing. So I'm going to change the number of points. There's so now if I look at this, so we're kind of getting our 5 block topology. And then the last step would be just kind of make it a little more uniform. Now if we okay, so moving on. Okay, so I'm going to disable that for now. So now we need to go ahead and assemble our measure block for these. Obviously, we do the structures when it takes them off. So what I want to do is the mesh. This is our AMI mesh. I'm going to put this in the front there and put it in 3. So we need to be able to assemble this mesh, we need to do it in 2 steps. We need to create the region between the AMI mesh, the rotor, and the inlet here. However, there's one thing we need to kind of avoid right now is that, I mean, again, you notice that the bottom of the housing doesn't have a hole for the shaft. But you have to turn on the rotor mesh, we have the bottom of the shaft, which is kind of coincident with the rotor, so we need to kind of fix that. So I'm going to get rid of that one, so that's not really part of the solution. And then we're going to add this hole to the bottom of the housing. So we're going to add an edge. Adding this edge is going to create that hole for us. So now we have this watertight collection of this mesh. What we can do is we can go ahead and send that. So again, to create the rotor region, I'm going to create the inlet, and then I'm going to just effectively walk my way down and just continue to assemble the region. So it's, again, the rotating region is going to be that interior region. We're going to have either dynamic mesh or MRF region. So I'm going to add the AMI mesh, the inner part of the bottom of the housing, and then the entire rotor mesh. So now I've changed my mesh type to unstructured. I should be able to assemble block it up. So it said, oh, it didn't create my mesh. So I got a problem. So this maybe goes to, I forget if that's the question. Let me go back to that's the question within this block assembly. That line will have the question about block assembly. So we're going to talk about since I tried to assemble that block, it's 0 blocks created, 27 dimensions. We can go and assemble the block manually. So we can do that by create, assemble special block, and we can just kind of walk through the block assembly. So I'm at in my region now, at the bottom, and you can see that as it's going along, it's kind of giving us suggestions for what it can assemble next. So I'm just go ahead. Oh, so there's the issue. So we have this orange region, which it's not bound to go by it. So what I can do is I can go and inspect the mesh there. To organize my housing mesh. What I can do is turn off the housing mesh and the rotor mesh. That way the issue is, and if I go to merge, so the tool you're going to want to use to be able to inspect if you're having issues with merge. So there we go. It's telling me that I have some connectors that are not merged together, so we can go and fix this automatically. It's probably one of these pair types, connect the connector or no connector. Oh, I forgot to show you. There we go. So we have a connector that's not sufficient. And this can happen when we don't have, we can have some kind of this. All right, now if I turn back the host connection, should be able to send it the connection. Okay. So I'm gonna go ahead and assemble the national. So again, that's manual block assembly. So that's kind of like if you can't figure out where what the issue is and can assembly block this. I'm going to do something for the housing region. For assemble a special block. So, okay, so we have two blocks. Huh? Lower block, I'll put that kind of a housing block. All right, so the last step here now is we need to populate. So again, this is something unique to Pointwise. Again, so we created this block, which is going to speak as the volume mesh. Now we have to populate it with the actual volume size. So it's a two-step process for unstructured volume meshes. And so we're going to do that using Pointwise's T-Rex method, which is its anisotropic pet measure. To be able to kind of set this up, we're going to do this first on the AMI domain. I like doing this kind of upfront because what happens is the AMI domain is going to kind of pierce through the actual fluid volume, and so the kind of the top and the bottom of the AMI are going to pierce through the boundary layer. So we're going to set that up kind of beforehand. So I'm going to set these values here, change the isotropic height to 0.7 because I want the layer in the software. The aspect ratio gets to 0.7. Set some boundary conditions here. The value 0.1, this is what we set before. Seconds. So we can see, oh, one thing I wanted to change here too. The other one I want to mention too, so we have these 2D quad cells in the boundary, but we have these hexes in the interior. I'm actually going to switch it to tries because the interior meshing algorithm of Pointwise is still a pet mesher and doesn't, and so it actually works better to use the try mesh for the interior rather than a pet mesher, because really the unstructured hex cells are going to occur on the boundary, not in the interior. So anywhere we think there's going to be interior mesh, we should just use the try mesh. That's what we want. So our step is going to be here. We're going to set up and use the T-Rex solver. We're going to say the number of layers is not important. Really, the important thing with number of layers is we want to set more layers than we think that it's going to create, because T-Rex will stop generating layers once the cells become isotropic and meet some sort of quality criteria. In this case here, our isotropic height is going to be 0.7. I'm going to say stop when the cells become 0.7. I find an isotropic height lower than 1 is better, because the volume of a hex is larger than the volume of that kind of for given plane spacing. So what we need to do now is we need to set boundary conditions for the T-Rex measure. So I'm going to set boundary condition for the AMI. And I want the mesh to the layering to match. I also want a boundary condition for the inlet outlet. And I want the same boundary condition. I want it to be match. Because what happens is I want the layering, to match up with the interior, right? So I want so there's some layering here created by the structured mesh on the inlet outlet, and this is how we're going to match up the structured mesh to the unstructured meshes using this match condition, where it just so happens that I've set the same growth parameters as I did with the structured mesh, so that's how it's going to match up. There's one more thing I'm going to do here is going to skip ahead, is that we have this small gap between the top of the rotor blades and the housing, and it's hard. And so I'm going to actually use the top of the rotor blades as a source, so basically a mesh source, to influence the resolution on the of the top of the housing. And so to do that, I'm going to create a new boundary condition. I'm going to call it walls or source. I'm going to change the type of wall, and I'm going to choose the adapt on, because what I'm going to do is I'm going to have the top of the rotor blades adapt the housing mesh. Right? So everything else now, I'm going to put in this wall boundary condition. So I'm going to go over here. I'm going to create a grid source. This is where the adaptation is going to work. So use the top of the rotor blades as a source to influence the. So what happens when the volume mesh runs is going to adapt the top. And I mean, ideally, you could say, well, why don't we just set everything to be grid source to itself? That can really slow down the calculation time. So I'm just going to do this a little more. So I think I got all that. Now, what I'm going to do is I'm going to go ahead and initialize the mesh. This is going to take about 5 minutes on my laptop, and I think I'm going to about 7 or 8 minutes left in my talk. So I'm going to finish off my talk while the mesh runs, and we can go into it. So I'm going to initialize it, and then I'm going to flip over my slides here. And let's just finish off here. Okay, so while the mesh is running, it's going to take about 5 minutes for me to do this. Is going to create about a mesh of about 6 or 7 million cells. So roughly on an old laptop, it's about a minute per million cells. So in this case, this is a workflow. Is creating the patch. We have to do this because we have to create the AMI patches. Pointwise doesn't have that AMI type, and it's CAE type. We have to scale the mesh. It's the renumber mesh that I really want to talk about, as well as some of the solver settings. So I'm going to kind of deal with this mesh types, and then there's some other steps. This kind of comes out of that. So again, standard practice. I always renumber the mesh. Every mesh I do. So why is that important? Because it reduces the matrix bandwidth and profile of the matrix. It almost always speeds up simulations, and there are some circumstances that it may result in solver error. And my colleague Darren has a more detailed explanation of what that means, and and how it affects it. I took a couple of images out of this blog post that kind of, here's the sparsity pattern on a really simple structure mesh before renumbering. Here it is after, and this is the IDD, and we want as many of the non-zero elements as close to the diagram as possible. And there have been situations where I've had like, 2 or 3,000 cell mesh that wouldn't run until I remember. And some of that has to do with just the way the grid is renumbered and Pointwise may be suitable for what it's doing, may not be suitable for cell. I find it particularly so for structured meshes where it's got some sort of computational order. And it's not very suitable for but even when I've used other meshes, block mesh or snappy mesh, I still find that there are some meshes. So just standard practice always remember. So in terms of mesh quality tips, my recommendation is to, again, when I say speed cells, I'm talking about in the open sense. Remove all highly speed cells. I talked about where they probably occur, round, sharp, convex corners, and the way to fix that is just the kind of surface mesh. And in any situation where I find where I have these highly speed cells, and I think the value is 4 with technical skill that is highly speed. In my experience, it's almost guaranteed to destroy the simulation slowly. So you really want to keep the skewness below value for it. Now I know there are some skew correction approaches for the interpolation. I think may improve solution accuracy, but my experience has been is that you just really need to move. On orthogonality, however, I found that you can do it. I know OpenFOAM can have a bit of a reputation for being sensitive to mesh, but I don't know. Over the years, I've come to learn that it's you can definitely run with orthogonal meshes. I generally find they occur in concave corners or adjacent surfaces of kind of a mismatch in size. So that's kind of the look and how to fix it. My rule of thumb is as long as you can kind of keep the number of highly non-orthogonal faces, so those are the faces that exceed 7 degrees. If you can keep that number kind of below about 0.1%, or let's say 1,000 faces in a million total, you're probably going to be okay. I generally, if I have faces exceeding 70 degrees, I use 2 non-orthogonal vectors. I find using more doesn't really help. Using less can give convergence. So 2 is kind of the recommended number. And I like to use potential foam as a proxy to help me find non-orthogonality issues, because sometimes it's like, is it my initial condition? Is it my mesh? Is it my boundary condition? What is it? Potential foam, since it's just a very basic Laplacian equation for the potential field, which has some very simple conditions. That's it. I find it is a nice, easy way to kind of like identify non-orthogonality issues. So basically, if the potential equation is stalling, it's most likely due to non-orthogonality. Whereas if you get decent convergence with potential foam, but then you go run your solver, it's going to be something else, probably boundary condition or initial condition. And I'm going to go to this here, but my last slide is that, Laplacian limiting should be used as a last resort. Like even on this mesh here, this blood pump mesh, which I end up with a few thousand faces over 70 degrees, some of them as high as 82, I don't need to use any Laplacian correction. This is actually my FD scene setup for that case where I have fully second order for momentum. I tend to just use first order for equivalence, but my choice. But again, Laplacian fully corrected, so even though I have non-orthogonality, if I'm fully correcting it, I should be maintaining the second order. Just another last kind of quick tip that I'll give you is it has to do with the solvers. The solver setup is for the structure equation, I like the stability of the conjugate gradient, but find it tends to be slow. Is that kind of a tip or trick is to use the multi-bit solver to be able to speed up convergence, or take advantage of the multi-bit without the penalty behind it. So I think I only have a minute left. So here's my contact information. I really apologize. This took a lot longer than I anticipated. Just had some issues, but still running. So I guess at that point, maybe I should just back to the slide so we can. So
there's a last question here. Can Pointwise create meshes with multiple domains for use in conjugate heat transfer? Yes, it absolutely can. And so just like I was showing today, I created a multiple region for a rotating region and a stationary region. There's no reason why that region couldn't have been a solid region or a region. So creating regions of multiple regions is perfectly fine. And so my mesh is finished. So I can examine that. So we can take a look at it really quick. So they were cut through enough, right? So you can see how everything is matching up at the inlet, which is structured. Everything's kind of automatic corners, all that kind of stuff. I see our non-orthogonality is a little bit high. We have some like in the 86-degree region, and that's because I think there's a mismatch between the mesh. We probably should refine our mesh a little bit on the bottom of the rotor and the bottom of the housing. You see our gap is pretty small, so the layers are flattened. So we talked about orthogonality in these equation regions right there. So this would just be all we need to just define the mesh right here. But as you can see that it's there's no reason why generating this mesh is going to take any more than about an hour. There's a lot of anyways, so yeah, so I think that kind of gets me towards the end of my talk. I apologize. I really apologize for that audio quality. I'm not sure what's going on. And anyways, so I'll put my contact information back up. And I'll stick around if there's any questions in the Q&A after, or you can send me an email. So again, thanks for your time.